Hi, my name is Ishan Mysore, and I'm a junior at the Harker Upper School in San Jose, California. My mentor for this Polygence project was Kevin Fry. With the rise of social media and the greater academic and peer pressures that students experience, I believe that maintaining strong mental health is becoming increasingly relevant. As a result, I wanted to create a model that could predict a risk factor for depression based on an adolescent's social media profile. I believe that this project will provide a valuable tool for early intervention of depression, ultimately improving the well-being of teenagers. Now, without further ado, let's get started. First, let's get some background information to help us understand the project context. Now, what is depression? Well, according to the American Psychiatric Association, depression is a common mental disorder that negatively affects how people feel, think, act, and perceive the world. However, depression is more than just routine mood fluctuation. Symptoms must be continuously present in order for a person to be diagnosed. Some common symptoms are the loss of interest in activities once enjoyed, fatigue and low energy, and a sense of worthlessness and delusional guilt. Symptoms of depression can impact nearly every area of an adolescent's life, including relationships with family, friends, and community. Recognizing the symptoms is a crucial step to providing the intervention needed for those who are struggling. In the 21st century, depression has become a critical public health issue, with studies showing a sharp increase in reported cases over the past decade. According to the World Health Organization, about 3.8% of the population, which accounts for 280 million people, experience depression. However, this percentage is a whopping 17% for adolescents. And these symptoms, if extreme, can invoke attempts at suicide, which is the fourth leading cause of death among those aged 15 to 29. Excessive social media use has also been linked to depression, as highlighted by a study from SDSU psychology professor Jean Twenge. According to the study, social media platforms promote competition among adolescents. For instance, adolescents feel pressured to see what others are doing without them, post things they're hesitant to post, worry excessively about likes and followers, and compare themselves to others and what they see online. And this competition can really worsen the discrepancy between an adolescent's actual experiences and their perceived notions for the future. As a result, adolescents can have inadequate perceptions of themselves and will thus feel depressed. Indeed, the risk of depression increased by 13% for each additional hour spent on social media. Now, despite the widespread prevalence of depression, there isn't enough being done at the early intervention stages. According to a survey, 20% of adolescents diagnosed with a mental health disorder claimed that they didn't receive the necessary therapy. Common obstacles to effective care, the World Health Organization reports, include a lack of investment, a lack of trained healthcare providers, and social stigma associated with mental health disorders. So this project aims to do the following. First, we'll gather and clean a dataset of labeled social media posts. Then we will train and optimize suitable machine learning models for text classification. And then we will deploy the best model to a website. If successful, this predictive model and accompanying website would significantly enhance early intervention efforts for adolescent depression in two ways. First, it would raise more awareness about social media's influence on depression. People will be more mindful of their social media usage, specifically what they post and view. And second, this project will maximize the percentage of depressed adolescents who actually receive treatment. Now let's actually get into the methodology for this project. I'll start by explaining how the dataset was prepared for training. So 11 datasets from Kaggle were used, and each dataset was modified to have two columns. One input column called post text, which basically contains the text of the social media post, and one target column called label. This column had two values. 0 means the post is not depressed, and 1 means the post is depressed. Then all of these modified Kaggle datasets were combined into one massive dataset. And after randomizing it several times, 80% of this massive dataset was allocated for model training, while 20% was allocated for model testing. Now, the training data needs to be in a clean state before it can be fed into any model, and thus a number of pre-processing techniques are employed. They transform the raw data into a suitable format for the model. So here are the pre-processing steps involved. First, all empty rows, punctuation, HTML tags, URLs, and stop words were removed. And stop words are basically the most common English words, such as the, and, or, and they don't really add much meaning to the overall sentiment of the post, so we can just go ahead and remove them. Then all characters were converted to lowercase, and then common chat abbreviations, such as LOL, were replaced with their full forms, so that would be laugh out loud. Also, all emojis were replaced with their textual representation, and finally, all the words were lemmatized. This means that each word was reduced to its base form. For example, let's say we have the sentence, the cats are running faster than the dogs. We would lemmatize that sentence to, the cats be run fast than the dog. And although this doesn't really make sense to us humans, it makes a lot of sense to the model, and it's gonna, as we see in the future, it's gonna make a much better prediction. So after pre-processing the data, the Tifidif vectorizer from scikit-learn was used to transform the text data into a matrix of floats. And Tifidif basically stands for term frequency / inverse document frequency. And we calculate the Tifidif score by first calculating two things. First is the term frequency, which refers to the frequency of a term in each row. Pretty simple. And then we calculate the inverse document frequency, which measures the importance of a term across the rows in a dataset. On the other hand, if a term appears in many rows, it is less significant. On the other hand, if a term appears in fewer rows, it is more significant. Then the Tifidif score is simply the product of the term frequency and inverse document frequency values. Now, during the process of vectorization, the Tifidif scores of each term are calculated and saved. Now that the dataset is clean, it's time to train models. One suitable model for text classification is a gradient-boosted classifier, which is a type of tree-based model. It uses the principle of gradient boosting. Now, you may ask, what is gradient boosting? Well, first the model makes an initial prediction, often with a shallow decision tree or weak learner. Then in each iteration, a new decision tree attempts to correct errors made by the previous trees. After that, the model is updated by adding the predictions of the new tree to the ensemble of previous trees. And finally, the end prediction is a weighted sum of the predictions from all trees. Now on the right, you can see some metrics here. We have accuracy, precision, and recall scores. And you can also see this grid, which is referred to as a confusion matrix. It helps see where the model did well and where it made mistakes. So of all the predicted posts containing depression, the precision score refers to the percentage of the posts that actually contain depression. In other words, precision is calculated as true positives divided by true positives plus false positive, which is the right-hand column over here. Now, of all the actual posts containing depression, the recall score refers to the percentage of posts that the model predicted depression for. In other words, recall is calculated as true positives, which is the right-hand box over here, divided by true positives plus false negatives, which is the bottom row. And as we see, the recall score is the most important because we would never want to miss classifying a person as depressed. So we're going to pay an extra attention to the recall score when we select the best model. So furthermore, another model for text classification is a random forest classifier, which is also a type of tree-based model. Random forest classifiers use the principle of bootstrap aggregation, or bagging. So how bootstrap aggregation works is that for each tree, the model selects a random subset of features that determine the best way to split the data. In other words, the model will select a few features that mark a clear distinction between posts containing depression and posts not containing depression. After that, each tree is grown to a certain depth, which is indicated by a hyperparameter. And then each tree in the forest makes a prediction for a given input. And the final prediction is a majority vote among all trees. So you can see the metrics over here. So the final model trained was a multi-layer perceptron, or an MLP. And unlike the two previous models, this is a type of deep learning model, or an artificial neural network. Here's how it works. So the boxes labeled x1, x2 to xn represent the input layer, and each box is a feature or an input value. The circles in the center represent the hidden layer. In this diagram, there's only one hidden layer, but the MLP used in the project contained multiple hidden layers. Each circle in the hidden layer contains inputs from all the neurons in the input layer. The lines connecting the input layer to the hidden layer are associated with weights, represented by the W's here. So for example, W11, W21. And these weights determine the influence of each input on the hidden layer neurons. Like we would probably want to put some more influence to some inputs over others. Then the hidden layer neurons sum up all the weighted inputs and apply an activation function. And this function basically decides whether the neuron should become active. Then the output from the hidden layer is passed as the input to the next hidden layer. And this process repeats until we hit the outer layer where the final predictions are made. Now let's take a look at the metrics over here. As you can see, the MLP performed pretty well in the training accuracy, 98.56. It's actually really good. However, we really care about the testing accuracy because we want to see how the model will perform on real-life predictions. We don't really care about how it performs on the data set it was trained. And as you can see here, the recall score is a little bit higher than the recall score of the other two models, which is a good thing because we would probably pay more attention to this model for choosing a model for deployment. Now, simply training models will not be effective. Each classification problem is unique and requires different configurations of a model to perform accurately. And thus, we must select a list of hyperparameters. And these are basically settings we choose before training a model. They guide how the model learns. Now, simply checking all possible hyperparameters, either by hand or by brute force, is really inefficient and time-consuming. So we can use a clever optimization method called Bayesian optimization. Instead of looping through all possible parameters, Bayesian optimization guesses smartly. It uses the information from a random guess to predict where the highest peak might be next. It also balances exploration and exploitation. Exploration means checking new and unexplored areas, while exploitation means focusing on areas that already look promising. As compared to the other optimization methods, for example, grid search CV and randomized search CV, Bayesian optimization finds the peak more efficiently with fewer guesses. So now that we've trained a couple models, it's time to deploy the best one. In this case, we've chosen to deploy the MLP. So in this website, users can enter their Twitter or Instagram handle, and then the website will scrape the 100 most recent posts and it will pre-process and vectorize them as mentioned previously. All these posts will then be fed into the model, which will assign a depression risk probability for each post. And based on the frequency of at-risk posts, the model will predict an overall risk factor. And then based on this risk factor, the application will provide links to raise more awareness and will suggest further course of action, for example, seeking a diagnosis or simply keeping an eye out for your symptoms. Now let's see a couple example predictions. This one is for mild risk of depression. First, the website states that don't rely entirely on this model because the predictions generated are merely probabilistic and they should never be used to substitute a diagnosis. This website's only used to highlight a need for more thorough assessment from a mental health provider. And since this person's only at mild risk, it's probably not necessary to seek a diagnosis, but really they should pay attention to how they're feeling. They should keep an eye out on their symptoms and they should reach out if symptoms escalate or they just need a helping hand. Now, this is an example prediction for severe risk, and this is where the model predicted a huge frequency of posts containing depression. In this case, it actually recommends the person to seek a formal diagnosis, and because their symptoms will have a major impact on their relationships in daily life, so they really need all the support they can get. And it also provides the National Crisis Lifeline at 988 if the person experiences a manic episode. So, as with all machine learning models, there are always ethical considerations involved. For example, users must consent to having their data collected, and this is stated in the website because users must make their account public and they must agree to having some of their posts scraped and fed into the model. It is also clearly communicated that the model could hallucinate, and this is stated because the website recommends that the person seeks a diagnosis and should not entirely rely on these predictions. Also, a diverse training data is collected from all continents, from all religions. We're not centering entirely on one sort of area. And finally, when suggesting professional help, the model always refers to credible sources. For example, the World Health Organization or the American Psychiatric Association. And this really adds credibility to the model's recommendations. And as previously stated, the application should never be used as a substitute for professional medical evaluation or treatment. Now, this project, if successful, will increase awareness for mental well-being as well as social media's influence on mental health. In addition, there will be a greater accessibility for mental health assessments in lower income regions, because 75% of people in low and middle income countries don't receive the necessary support if they are diagnosed with a mental health condition. In addition, there's an enhancement of early intervention efforts for adolescent depression. And if this model is successfully integrated with mental health platforms such as Scout by Sutter Health, it would provide a seamless connection between at-risk teens and mental health professionals. Thank you for listening. If you have any questions, please email me at ishanmysore@gmail.com or check out the research paper in the link below. Thanks for listening.